Okay, good evening, everyone, and thank you very much for allowing me to talk. My name's Brian Moffatt. I'm a Pvt consultant, and I would call myself a petroleum detective. We do lots of investigative work, trying to sort out problems with oil and gas, characterizing them, trying to understand what we've got. And I was asked this evening to talk particularly about making sure that things are all right, making sure that the fluids that we're studying are right, and that our characterization and descriptions of them are indeed correct. This is a picture of us taken a few years ago. My colleague, co-director Mike Fawcett assigned me, and other workers. And we've studied a large range of Pvt related, reservoir fluid related and I'm going to start on where we need the information, because it's not just Pvt, we have a sample, we make a black oil table and we forget about it. It's useful across a wide range of areas. So in exploration, we need composition for economics, how reservoirs fill, fluid relationships. We need it during the appraisal stage. We've had contaminants and flow assurance. In development, is our development working as we wish? Do we have the right phase behavior? Is our reservoir model working correctly? And for production, composition modeling, can we predict sales streams? So these are all very important issues. And I'm going to be talking about this throughout the talk, and how we can move across different disciplines as well, and how it all fits together. 35 minutes on this talk, and I'm going to put the conclusions in then, because I know an hour is quite a long time for a lot of people. And then after that, I will put some case studies in. So if you haven't got a full hour, that doesn't matter. You'll get the gist of it in the first 35 minutes. So what's the usual story? Well, the usual story from the perspective of a petroleum engineer developing a field is that the field will be tested. So we will typically either flow to surface or take subsurface samples. And then we would take samples and take those samples to the laboratory, cook them up to reservoir conditions, and measure all the properties that we think we need to help us plan our development. That will give us information such as viscosity, or in this case, liquid saturation. How much liquid actually falls out of the reservoir fluid as it's going to be depleted? Is it worth going to be doing gas cycling to try and get more liquids out, or EOR, things like that? So we need some physical data to start with. Then we can encapsulate that, put it in our reservoir simulation model, and from that we can make our predictions of production forecasts for gas or for oil, or both. And that picture is pretty much what I think most people consider as Pvt and where it fits in. And so for here, it's going to fit in all the way from sampling, things that are going wrong, and particularly from the lab experiments to the reservoir simulator. And one of the things I want to show in the talk is this is a very limited view of Pvt, and I particularly want to impress on you how to try and get the data correctly, but also how the data can be used to great advantage in a wider application than this. And this is something that the industry is really missing out on. So what is the scope of our fluid studies? Is it just Pvt, back oil studies? What are we going to do? Well, these are conventional, the standard Pvt studies. And a lot of these have survived industry for years and years. And I think some of them, to be honest, are getting beyond this sell-by date. Differential liberation, that's fairly useful. Constant volume depletion, I think less so. Why do we do constant volume depletion so much? And people say, oh, well, it models how the reservoir depletes. And we say, well, how many reservoirs in the world have been modeled in this stepwise fashion in a constant volume depletion? And the answer is none at all. We don't actually use the constant volume depletion anymore to model the depletion of the reservoir as it was done before the age of computers. No, what we do is we take the information and use it to tune our equation of state. And then we use our equation of state to predict the properties continuously. Well, there's a question. If we're using the data to tune our equation of state, is this CVD still the best study to do that? In fact, it's not. If you really want accurate information, it's much better to do a few equilibrium flashes at fixed pressure. It's like doing a constant composition expansion and stopping and measuring both phases. And if you do that, you can get direct measurements for both phases. And it's better for tuning an equation of state. So how do we order out PVD studies? Most of the industry works like this. We've done diff libs and CVDs before. We've always done them, so we're always going to do them. But if we do that, we'll still have the same problems that we've always had. So here's our, imagine a oilman ordering up a study as though it was a drink in a bar. The fluids testing domain, we can do all sorts of experiments specialized to target particular problems that we might have with our reservoir. We might have particularly for EOR, all sorts of studies there, for flow assurance, for dealing with contaminants. And most of this information we collect, we characterize, and we focus it towards our field development. Or indeed, if problems surface during production, we can tune these to those then. So Pvt Data Qc. So we've got our information, we've got our PVT report. The numbers are there to 4 or 5 decimal places sometimes. Is it any good? How do we know? Well, traditional Pvt Data Qc looks something like this. So we have 3 branches: our sampling conditions, what was happening at the well characteristics, the field data versus the lab. The central branch on here, sample quality, and this is where the biggest focus is. Is the samples contaminated? Does it have air? Are the opening pressures correct? Are the compositions looking sensible? Equilibrium plots, these are very useful diagnostics, and I shall touch on that soon. And the lab measurements consistency. Material balance, if you do a differential liberation or a CVD, you can look at all the components in there, and everything you put in the cell should balance with what you take out of the cell at the end of the study, and it probably won't because nothing's perfect. But that is very commonly used as a check. Is it useful? Well, not very. It's a lot of people say, oh, this is what you do, but in fact it's not very valuable information. The overall mass balance is useful, but supposing something is wrong, supposing, I don't know, you get less C5 out than you put in, well, where in the study has it gone wrong? We don't know. It may be we have an erratic point, but because of the stepwise nature of the CVD, errors from one depletion level cascade into the next and the next and the next. And people plot the K values out of a CVD experiment and say, well, it looks about right, but really we've no way of telling. This is why equilibrium flashes are better, because you can nail every phase and get a much better description for your equation of state. You don't have this progression of errors spilling out from one level to the next. But there's something missing here. Supposing we did a CVD experiment and we did a mass balance study on it, and it came out perfectly. We say, wonderful, we've got 100% mass balance there. It must be a good sample. Well, is it? It may or it may not be. The best it can tell us is that the sample that we put in the cell, we have done a good study on. Does that mean that it's a good sample of the reservoir fluids? No, it doesn't. At best, with good sampling, it might tell us it's a good representation of the well stream fluid. But if we're pulling hard on the reservoir, we've gone through a bubble point or a dew point, then what we're flowing up the well bore isn't anymore the same as what's in the reservoir fluid. So we need to do something more than that. We need to add this overarching stage. We need to look at the Pvt data quality checks in the context of how they were sampled, in the context of the well test. We have to ask ourselves, do the data make sense in the context? And I shall show you an interesting example applying this. Sampling issues. So even when we've sorted what we've just talked about, there are still issues. Some of them are downhole and some of them are surface. We'll look at downhole problems first. And there's all sorts of problems that can befall taking this. We may have a compositional gradient in the reservoir. We may have gas breakout and relative permeability effects. We may have gas coning. We may have perforated across more than one zone, so we are getting commingled flow. We may have insufficient flow for all the fluids to be sneezed to the surface and captured, so the well might be coughing, gargling. A lot of these things we can't do anything about, but when we come to review the data, what we are going to look for is coherence in the data. Does everything make sense together? Because a lot of the problems here, we can actually work back. We can imagine what the problem was and see if we can model that, if we can interpret what had gone wrong, and that is then still consistent with the data. We can take tests from bottom hole sampling or formation testers. We can get a lot of information from these. We can get the pressure gradient, which is from which we can infer the downhole fluid density. And indeed, if there's more than one fluid, we may find a gas gradient and an oil gradient and a water gradient. We can get some compositions. These are sometimes oil-based mud contaminated. And sometimes these probe devices fail to make a good seal against the formation, but they are useful. If they are oil-based mud contaminated, if you look at the trace on the left, here's an example of an oil-based mud contaminated sample. So we have the background trend of hydrocarbons, and then we have this big peak. This is a diesel type based oil that's been contaminated. So we have this very exaggerated peak around C11, C12, and C13. And there are ways that we can tackle this to try and eliminate it's in the composition. Of course, we can't physically decontaminate the sample. We can only measure what we've taken. But if we take measurements of the sample, model that, we can then change the composition and make predictions of what the properties would be without the oil. And if the amount of contamination is small, this can be quite successful. We can use other tools to help us decide whether the downhole samples are good or not. We can make predictions of phase behavior, as in the top right-hand corner. Is our sample, does it intersect reservoir conditions, the phase boundary or not? And then we'll come to an example of that soon. We can compare the fluid densities derived from the pressure depth gradient with our lab values, and if they tie in well, then that's very good information. If they're different, we'll need to know why they're different. Is there stuff that we can still learn, even if they're different? What about at surface, flowing samples to surface? Well, still room for problems here. In terms of contaminants, we may lose reactive components to the tubing or even release it. So if we're testing a well which has low levels of H2S, it may take a long time for that to saturate the metal tubing, do we actually get a reading? It may flow for several hours, then it just creep up slowly. Or if there's a lot of H2S there, this will quickly coat it and it will come screaming in, rapidly plateau. Mercury is another contaminant that is very prone to difficulty in sampling. There can be mercury compounds in the drilling mud, so it's possible to actually introduce the contaminant from drilling activities and then monitor how that changes with time during well test cleanup. We may get separator instability as changes in the gas-oil ratio. We may get liquid carryover. There may be poor samples taken. It doesn't happen very much these days. It was more prevalent in the past. One of the biggest problems associated with separator samples, which is hardly ever mentioned in the industry, and I have no idea because it's quite common, but that is when you have a very hot separator. If your separator is running at 70, 80, 90, 100 degrees centigrade, this is really hot. You couldn't just lean up against the separator and put your hand on it. You'd severely burn it. If you try and sample the liquid from that, well, that's fine, because its bubble point is going to be at separator conditions, and you're sampling it into a cold bottle, so that will be fine. But the gas will have its dew point at 80 or 90 degrees centigrade, and you try and sample that into a cold bottle, a lot of the liquid will fall out. You can take the bottle back to the laboratory and try and heat it up, but there's a lot of liquid to try and revaporize. You may not be able to cook the bottle to that temperature. It may be beyond the temperature rating, and that's something that we find very often with hot separators, that when you recombine the apparent gas with the liquid compositions, there's a bit missing. And if you make predictions of condensate yields based on this flow stream, you will quite severely underestimate your liquid yield. Other problems with surface sampling, or not so much a problem, but something to be aware of, is that there's a kind of myth in the industry that any field, any oil or gas condensate has a GOR, as though it's somehow chiseled into the fluid. And that's nonsense. GORs, gas condensate ratios, are always condition dependent. The little graph here gives an example of a lean fluid and the predicted condensate gas ratio that you would get at two temperatures. We've got 30 degrees centigrade and 50 degrees centigrade. So it's just one fluid coming into the separator at different pressures. And you can see for the 30 degree one, you can get up to 7 barrels per million standard cubic feet at 30 degrees C and about 60 bar. Much hotter, much higher pressure, and you would see nothing. Now that shouldn't matter if we're recombining fluids, because whatever goes in the liquid, whatever doesn't go in the liquid must end up in the gas. So if you recombine them, you should end up back to the initial reservoir condition. But practically, it's actually better to try and get more liquid. You've actually got something to handle and to measure and to operate the turbines, the flow meters. So there are practical considerations where you need to bear in mind to get the most accurate composition. And surface readings can be very problematic as well. The well will be starting, stopping, shutting in. You may find a lot of scatter in, for instance, the condensate gas ratio. This is a well test, and here are the gas-oil ratios plotted against the wellhead pressure. And you can see there's a vast amount of scatter there. So which one's the right answer? Well, we're going to show you how to work this out for this example in a bit. So what tools can we use to help us? The equilibrium plots are really useful for this. I would always recommend doing these. A lot of Pvt reports actually include them as default, and do look at them, do make use of them. What does it tell us? Well, if we've got gas and condensate or gas and oil flowing through a separator, we expect, for instance, methane. We would expect more methane in the gas than in the liquid, and this is true for all the components. And the ratio, which is the K value, the ratio of the molar concentration of a component, methane, in the gas divided by the concentration in the liquid, the K value, those K values for all the components should form an anticipated trend, and that trend was predicted on this Hoffman-Hocott equilibrium plot. So we can take our gas composition, our liquid composition, and we can work out the K values for those. We can put our recombined fluid in an equation state package and actually calculate the K values. And this is very, very easy and pretty accurate for most separator conditions. And if the two overlie, then that's a very good indication that not only are the compositions good, the analyses, but also that they are consistent with the separator conditions. And that's important, because if those are correct, then the calculations that we get to work out the gas oil ratios are correct, and we can be fairly confident about the composition. If you get a lot of spray, if the flow rates aren't really designed for the separator that you're using, you can get carryover, and that can show as the green dotted line here. But the examples that I spoke about earlier, where you have a very hot separator, you tend to get this droop down. For the heavier components, they fall below the theoretical line. So it's marked there, trend for heavy end losses. So that would be typical for a very hot separator, where we've actually lost some of those components because the sampling equipment was cool and we don't have the capacity to really roast those up to try and get them single phase again in the separator. But here's the thing, because we know what they should be theoretically, we can actually correct for that. So this is a really useful tool, because it not only shows if the compositions are consistent with the separator conditions and are correct, but if they're wrong, in many cases you can correct them, which is much better than you can say for the constant volume depletion study. So we're going to look at some examples. So I've explained about the traditional QC, about applying it in context. So these are real case studies that we're going to have a look at some examples of. And the first example, this is some work we did for a client. The client had run a well test of a fairly lean condensate and very wisely taken samples both at the surface from a separator, but also from a bottom hole sample. And if we plot the compositions out, here they are plotted on a log scale, there is a very large difference between the C7 plus amounts between the bottom hole sample and the separator samples. The bottom hole sample was much leaner. I think there's about 2.5 times more C7 plus in the separator samples compared to the bottom hole sample. And the client, not unreasonably, said, well, it's two different fluids here. Which one's right and which one's wrong? And can we work it out? And can we use the tools that we've seen to help us? These are the gas oil ratios plotted against wellhead pressure. And that's useless. It's just showing a scatter. Are there other ways that we can use the information to try and get a better handle on what we're dealing with here? Let's try plotting gas oil ratio against flow rate. Again, a scatter. We can see our bottom hole sample now, separator samples, just in amongst the scattered points. What about GOR against wellhead pressure? Again, this isn't helpful. It just shows a wide scatter. Do we believe all the points? Well, some of them we can, most of them we can, but at the moment, the information isn't in a useful form that we can extract. The client initially thought that the bottom hole samples would be likely to be better. Why? Because it's a bottom hole sample and hasn't been subjected to any recombination errors or measurement errors. And secondly, because the phase envelope predicted for the separator condensate samples, recombined samples, actually came out slightly above reservoir conditions. And physically they can't. If you can't have something that's more than saturated at reservoir conditions if you're flowing single phase. So that was the initial presumption. Can we improve on that? Well, we can. What we can do here is we can take our flow periods, and each flow period, as it went through the separator was operating at a different temperature and pressure. And that's not surprising, because the reservoir fluids come up. If it's flowing fast, it'll deliver heat faster at the surface. The separator pressure will be higher, and you'll get more flow through. So what we've done here is we've taken the field measurement GORs. We've taken our recombined samples in green, using one composition, and we've used the bottom hole composition as the brown dots, and we've plotted what we would predict. And this is where we're actually acting as petroleum detectives, and we're getting now a lot of information that's really useful. What does this graph show us? Well, that red line is y equals x. So if the predictions are very good, it means we are accurately predicting from our little equation state model of our fluid composition what the gas oil ratio is. And below 30,000 centicubic feet per barrel, it's very good match through those points. So our separator condensate, we can believe it because we make our little equation state model of that, and we can use it and we can predict it. And we know it operates over quite a range of flows. But what about above 30,000? It plateaus off. What is that telling us? Well, if you remember the phase diagram plot, what we're doing is we're actually falling into the two-phase region. Our pressure around the wellbore has fallen below the dew point. We are depositing condensate in the reservoir, so what we are producing to surface is much leaner. So it's telling us that if we flow much faster, we're not going to keep that up. We will lose condensate. So what this tells us is two things. One is that the separator condensate compositions are correct, and that the bottom hole sample was incorrect, but it also tells us how we can manage our wells and the production, the condensate that we can get from that as a function of the rate. So this information not only tells us the fluid, but it helps us for the field development. So that tells us what I've just said. We're going to have a look at a different sample now. This was a strange gas condensate, very strange. The client came to us and said, we've got this really strange gas condensate. We've done our PVT, we've done our constant composition, constant expansion, CVD, the mass balance of the CVD came out really good. But the fluids that we get, we can't match that against the well test rates. It makes no sense. And again, samples were taken at surface, samples were taken downhole. If we compare the compositions here, there's a wide spread. Two of them, the blue and the green points, overlap. So it was kind of felt by the client that those were likely to be right because at least two agreed. But that was as far as it went. There was no more thought to it than that, and it was left as a problem. There were several flow periods to surface during this well, and the graph on the right shows you the different GORs for the different flow periods. And they are up and down all over the place. So you can't really say, well, this one must be right. It's not obvious from this plot, from the way that the data are presented. What else do we know about this field? Well, it was a fairly tight reservoir, low permeability. It did eventually stabilize out at around 8,000 standard cubic feet per barrel. And in the Pvt cell, as you would expect for 8,000 standard cubic feet per barrel, it gave a condensate. Gave up to about 25% liquid saturation. But here's the thing, the dew point's at nearly 6,000 psi. The reservoir pressure's below 4,000 psi. So whatever this strange gas condensate is, it can't be representative of the reservoir fluid. If it was truly representative, the highest the dew point could be would be the same as the reservoir pressure. You can't be more than saturated. So what is going on here? The trick is to plot the data that we can really understand what's going on, as we did in the previous case. But in this case, we're changing things slightly. What we're doing is plotting the gas oil rate, that's on the y-axis, the gas oil ratio on the y-axis against the gas rate. And it's quite clear that the faster we flow the well, the higher the gas oil ratio. Well, that immediately makes us think that, well, it's not a constant composition. Why would that change? And the obvious answer is that the harder we pull on the well, the lower the pressure around the well bore. So the more solution gas comes out of solution, that is less viscous than the oil, so that races ahead of the oil, rushes up the well bore. So what we're doing is, it seems we're depleting a volatile oil. It's not a gas condensate at all. If that's true, then what we can do is to extrapolate back to zero rate, and that should give the initial fluid. So we took our Pvt study, modeled our fluid at whichever gas oil ratio it was, used the tuned model and worked out what the composition would be at, I think it's just over 2,000 standard cubic feet per barrel, and then asked the model what would be the bubble point at this condition, and it came out very closely to the reservoir pressure. So this was the answer. By actually turning the data around like this and plotting it, we can work out what the initial fluid was. We can use our equation of state model to predict the initial fluid properties. And indeed, this did prove to be a volatile oil rather than a gas condensate. But the clues were there. It's just picking up on them. For one thing, the condensate was black. And condensates, well, they can be dark, but really oily black should give clues. How are we doing for time? All right. So, well, just this really for amusement. So we're going to do a bit of QC. You'll be in a job. You may get samples coming in, people asking about them. How do we know whether any sample is? So I'm not going to actually show you a real sample. I'm going to do it by analogy. So we take a sample and we look at it and we say, is it any good? Is that what a sample's looking like? And any resemblance to the foreign minister is purely accidental, I assure you. So is that what it's supposed to look like? We don't know. Let's take some more samples. Now we've got several samples. Yes, there's variation there, but we're getting the feel of what it is. But it doesn't always work like this, because we may get things that look like samples that actually aren't. It might be drilling mud, a mud filtrate, or anything. So we may get things that we think look like the sample, but really are not at all. Is the reservoir depleting as we would expect? The pressure falls, the fluids change. We would have our model, our prediction. Is it going to plan? Well, sometimes it does. Sometimes it doesn't. The normal progress has stopped here completely. I don't know why. The bicycle stopped moving. I don't know what's going on, but there's no further progress. We have to be petroleum detectives and find out what's going on. And sometimes things just get so strange, we can't understand what's going on at all. So now you have to be a really good petroleum detective and go into the background and try and understand the factors that led up to this. And what are we as petroleum detectives trying to do? We look at all these data, we try and understand them, understand where they fit in, and we want to condense it down into something very simple. So a simple formula, something that's binary, something that we can then use in our modeling, so something like that. So to conclude here, issues, main problems, gas-oil ratio measurements, phase behavior from poor samples. Yes, beware of modeling heavy oil viscosities and compressibilities. Be aware, contaminants. These are quite often overlooked. Wax scale, deposition, information that's going to be needed in the development plan. Compositions, you get different compositions from one reservoir. Well, what does that mean? Do you have a compositional gradient? Possibly. Do you have different compartments? Possibly. You need to be looking at the data to try and work out what's reasonable, what's likely. Are there other indications that we can get from this? It's very lean condensates. These can be really troublesome. It's very hard to measure the amount. It may be below the meter range, and yet we've got to deal with it. It's not, you can't just ignore it. It'll accumulate in pipelines. So how do we configure our test to try and get more liquid out, to get a better handle on it? The last point here, placing the Pvt in context. That's actually one of the best methods of data QC and what we should really be doing. It's like saying, well, we've done our test, here's our Pvt sample, that's it. Well, it might be it for that moment. What about the rest of the test? Does that sample fit in with the samples that were previous to that? For the different flow periods, can we model those with the same composition? Does it work? So rather than looking at the data as though it was a snapshot from a camera, view the data more as though the whole well test was a movie, and we want to understand the whole story, because that's much more powerful, that's much more useful information. If you're new to this, how do you approach it? So even before you start, what are the objectives? What are you trying to achieve? Do you have enough information at your fingertips to make a confident answer? Who wants to know? Who are the stakeholders? Is it process engineering, geologists, feed design? Is it for sales or reserves reporting or forecasting? Which tests are really appropriate? And here we got objectives versus workflow. This is really important. I see a lot of people saying, oh, I've got this this fluid and they need to make a Pvt model of it. How do I group it all together? I said, well, why do you want to group it together? Said, well, because that's what you do. That's what the workflow is. Do you need to do it for that purpose? Every time you group things, you reduce the definition of the information. Can you use it ungrouped? always consider what your objectives are and whether you're working towards doing that or whether you're blindly following a workflow. Workflows can be very useful, but they can also blind you into working in a certain direction because you think that's what goes on. Units and definitions. This is one that traps a lot of people. It's like when I said at the beginning that a gas-oil ratio is something that we think is somehow chiseled onto an oil. Formation volume factor, B0, what's that? That's the relationship of the ratio, that's the ratio of the volume of oil in the reservoir to what we produce at the surface. And when you look at PVT reports, you'll find different values of this. You'll get a different value from differential liberation. Why? Because the oil is formed at reservoir temperature, for one thing. You'll get a different answer if it goes through a separator test. You'll get a different answer again if you analyze a bottom hole sample and flash it to atmospheric pressure and say 120 Fahrenheit. Why are they all different? Because they're all flashed at different temperatures. So be careful. Make sure that you're always comparing like with like. Does it matter having three? Which ones should you use? Well, all three are useful because if you account for the conditions, you should find that they're all the same. They should end up with the same composition, and you should be able to predict given the conditions. Data coherence. Next point there. This is what I was saying about all the pieces fitting together. It's like every piece of information you take is like a jigsaw piece. And when you put them all together, it ought to make a picture. Do they? Ask yourself. Challenge the data. Of course, ask for advice. Ask for management, labs, external advice. Don't just rely on workflows. So at the end of this, there's all sorts of conclusions I could leave you, but I only want to leave you with three, because I think these are really important and the bits that really should be you take. If you take away nothing from this than these three, then it's been worthwhile. So one, think about your objectives. What are you trying to achieve? What's the purpose of it? From that, decide the tests that you're going to apply. When you've got the data, then put your petroleum detective hat on and look at it very carefully. Second point, work sense, not workflow. Make sure the work you're doing is actually supporting your objectives. Don't just follow some rule about grouping components, or you have to do a diff lib or CVD because it's an oil or it's a condensate. Think, what are you trying to achieve? What information is really most useful? And ask for that. And if you don't know, well, ask the labs, ask around. And finally, challenge everything. There's all sorts of data and myths in the industry. Use your own judgment. Ask for help, challenge it. Say, well, is this right? Mind you, this dew point's higher than the reservoir pressure. That's to be challenged. So hopefully, in ordering work and taking understanding, we change from the picture on the right. Well, we get rid of that. So how are we doing? That's about it. I think I'll stop there. I've been talking for almost an hour, and I will take questions. Hello. Hello. Right, I've got a question here. The question is, if we have a critical fluid at a saturated oil reservoir, what is the best method to take a sample, bottom hole or surface sample? Good question. I would take both. The example that I showed you, the second example, where we had the gas-oil ratio all over the place, we could use those information, those data, to work back to what the fluid should be without any drawdown. It should be possible to take decent bottom hole samples of near critical fluids, but practically they are very fraught with difficulties, more than you would expect. However, if you take several, you can work on those fluids. So if you suspect that you've got a near critical fluid, it may have a gas cap, it may not. It may be slightly richer below the gas oil contact. So if you get a good analysis of the fluid and you have a good Pvt study, you can do two things. You can tune to what you have and make predictions. So for instance, if you think you're close to the gas oil contact, you can actually work out what the composition would be at the gas oil contact. And if it's surface samples and you've flowed below the bulb point, what you can do is to recombine them at the flowing ratio in the separator into your Pvt cell, and it will form two phases in your Pvt cell at reservoir conditions. The relative volume of the gas and the oil will represent the relative volumes of the gas and oil that flowed into the wellbore at the reservoir pressure, not the pressure that was flowing during drawdown, but corrected to the initial reservoir fluid, because you're actually cooking it back up to reservoir conditions. So that will give you your gas cap and your oil from that experiment. So you could separate those and actually do a condensate study on the condensate and an oil study on the oil. Here's another question. For recombination, how can we use Hoffman plot to validate the GOR? You can't. What the Hoffman plot does, it checks the composition of each component in the plot. Well, for the gas and the oil, it checks whether they are consistent with each other at the separator conditions. Imagine this: you have a cell, Pvt cell, and it's in equilibrium. So you've got gas and condensate there. It's in equilibrium, and you analyze each phase, and you do a plot, and you get a nice straight line. What happens if you then halve the gas volume in the cell? What's going to change? Nothing. You've just got half the gas, but the equilibrium isn't going to change. The equilibrium is going to be fixed by the composition and the temperature and the pressure. It doesn't matter how much gas is there, whether you had 2 inches or 10 kilometers above the contact. As long as the composition is the same, it's not going to change the equilibrium. It's the one thing the equilibrium plot that doesn't give you is the GOR. Can I share my cam? Screen share? Yes, I think so. Does that work? Yes. A lot of disappointed people out there. Hi. Any other questions? Actually, can someone tell me whether this is going out? Is this other questions being heard out there? Here's another question. Good. This is exciting. For PV tests, what is the workflow sense you prefer to adjust DDL to SEP conditions? And what do you think of the McCain latest adjustment equations? There's two parts to this. You need to do the well. Let's go back to what we're about here. We're getting this information to achieve some objective. So it might be we want to develop our field, we want to design our separators, or we want to make our sales predictions. If we have our PVT study, we can use our equation state to tune our model to that. We might include some separator tests. Those separator tests may or may not be at the eventual production conditions. Doesn't matter if it's not exactly the same. We have a lot of calibration data that we can tune our model to. So we can then use our tuned model to predict the gas oil ratio to whichever separator conditions that we want to test, and that's the way to do it. What do I think of the McCain latest 2003 adjustment equations? I don't know. I haven't seen them. If you get a good tuned model, you can actually predict it with your model, and I don't see that there's any need for anything else. Thank you. Is that the end? I can't hear anything, so I'm going blind here. Here's another question. How can I prove compartmentalization from Pvt analysis if we speak about the same gas? You can't prove it just from the same gas. You have to act as petroleum detective again. What are the clues you can get for compartmentalization? You can look for different subtle changes in composition. The best method is actually pressure testing. If you pressure test on this compartment, does the other one remain unchanged? That's probably about the most useful. Link in geology, look at the pressure gradients. Are they consistent across the different zones? So yes, you need to review the compositional data, the pressure depth plots, geology, review the whole lot together. Well test, of course, well test analysis. If we deplete one side, does that show up on the other side? It is difficult because you may get pressure communication via an aquifer. So the two gases may actually be not in communication with each other across a gas, but they may be in pressure communication via a shared aquifer. But the pressure response time for that will be much slower. So it's not easy. But the pressure offset's probably the most important one. Right. Here's another question. Could you elaborate more about dynamic Pvt behavior used in reservoir simulation? Meaning, in saturated reservoir, we have two ways of curve behavior. What I was meaning there was that, oh, there's more. Right, oh, right. In saturated, we have two ways of B0 curve behavior. Not quite sure I understand that. But it goes back to, if you've got a good composition, you've got a reliable PVT study of it, you use that to model your fluid, and then you use the model to predict. What is your recommended workflow to match the viscosity of heavy crude, especially those having waxes? Gosh, the questions are flowing in fast now. The waxes, look at, well, that divides into two. Are you getting waxes downhole in the reservoir or just at surface? If they're at surface, there are rheology tests. You need to take the measurements of the fluids at nearby conditions for what you want to study, and you should be able to correlate the measurements with a fluid model and according to the flow type. Waxes, they can be difficult because the viscosity will depend on how the wax crystals are formed. So if they're cooled slowly, they will be different from very quick cooling. So the rate of heat loss is important. Another question, for example, when the original reservoir pressure declined from above peak bubble point, and when we perform water flooding and pressure increases again, but we get another bubble point, you can change the bubble point locally if you go below bubble point. So you have your accumulation, you lower the pressure, you form a gas cap, you then do your water flood, you increase the pressure, and some of that gas will then redissolve locally, but it doesn't have time to diffuse throughout the reservoir. That takes geological time, millions of years. So where the pressure has increased and you've got some of that gas redissolved, that will have a higher bubble point. There could be other reasons. You could have a gradient of compositions, and actually through producing oil moved something that was of different properties to be produced. Another question, which is good sampling method for heavy oil reservoirs, either surface or bottom hole sample? Neither. If you can go through a separator, you have a good chance of getting a gas oil ratio and recombining the samples. Bottom hole samples can be very tricky with heavy oils. You can try it. I've not seen very much success with it. It can be very variable. If the reservoir is deeper and hotter, it can be more mobile and you can have success. So I would try both if you can, but certainly if you can recombine surface samples, you have a better time averaged view of what's going on. So you model measure the gas oil ratio over time. Is it constant? The longer, the more the well is produced, the better will be the sample. So the gas oil ratio. So you can then use that gas oil ratio to reconstitute. From your experience, how do you evaluate the optical fluid analyzer and the real-time downhole sampling methods? I found the real-time downhole sampling methods have been very good, and the sort of samplers that remove a lot of contamination potential by having this annular ring that sucks fluid in and discards it around the sampling point so that the sampling point is cleaner. Those have proved very useful. The optical fluid analyzers seem good and bad. They do work well in fields that are very well known and understood. So if you're doing infill wells, that's been good. I've seen variable results in wildcat wells, though nothing very recently, so they may well have improved. The most recent ones I saw was for a difficult fluid in that it was a gas condensate, and the data came out in two sets. Some of them said one set said the reservoir fluid had a density of 0.6 grams per cc, and the other set said it was 0.45 grams per cc. But they were either in one camp or the other. There was nothing in between. It was either one or the other, which suggests to me that there was some algorithm looking at the data, and one said, oh, it's a condensate, it's this, oh, it's an oil, it's that. And so we had to work out which one was correct from that. So it was of some use. I think they will get better. So that's that. Any more questions? No more questions. Well, thank you very much. I hope you found it interesting. Oh, no, I can end the session. Well, goodbye. Thank you very much, folks. I hope you found it interesting. Any queries, brian@petrophase.com. I'm there. Or there's the LinkedIn forum, often on there answering questions as well. But thank you for your interest. Bye.